Good evening, friends. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's the universe whispering something we've forgotten how to hear. Tonight, we're going to think about darkness. Not the gentle darkness that wraps around your bedroom at night, soft and familiar, but a different kind. The kind that bends light. The kind that swallows time. The kind that could, if it wandered close enough, change everything we know about being here on this small blue world under these patient stars. What if darkness itself could travel? What if it could move through space silent and invisible, pulling the fabric of reality along with it? What would happen if a black hole passed near Earth? Before we drift into that question together, I want to say something. If you find comfort in these quiet journeys through science and wonder, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. These conversations mean something to me, and having you here listening makes them feel less like shouting into the void and more like sharing something sacred in the dark. Now, let's drift. The universe is full of objects we can see. Planets that glow in reflected sunlight. Stars that burn with their own fire. Galaxies that spiral like frozen whirlpools across billions of light years. But scattered among all that light hidden in the spaces between are objects that don't reflect anything. Objects that don't shine. Objects that exist only as absence is hunger, as the place where something used to be and now isn't. Black holes. Scientists suggest that our Milky Way galaxy alone contains hundreds of millions of them. Most are stellar mass black holes born when massive stars perhaps 20, 30, or even 50 times the mass of our sun, reach the end of their lives and collapse inward all that matter, crushing down into a space so small and dense that it breaks the rules of everything we thought we understood about how things work. Some black holes are larger, much larger. At the center of nearly every major galaxy research shows sits a supermassive black hole containing millions or even billions of times the mass of the sun. Our own galaxy's heart holds one Sagittarius A, pronounced Sagittarius A star, a giant with about 4.3 million solar masses sitting quietly 26,000 light years away so far that its light takes millennia to reach us. And by the time it does, we're seeing not what it is now, but what it was when our ancestors were painting caves and telling their own stories about the stars. The term black hole wasn't coined until 1964 by a journalist named Anne Ewing, though the idea is older, much older. Back in 1796, a French mathematician named Pierre-Simon Laplace wondered what would happen if a star were so massive that not even light could escape its surface. He called these theoretical objects dark stars. It was a thought experiment, a mathematical curiosity, something to ponder, but not something anyone expected to find. Then Einstein came along. His theory of general relativity, published in 1915, showed that gravity isn't a force pulling on things. It's the shape of space and time themselves bent and curved by mass. A heavy object doesn't pull on you. It creates a dip in space-time, and you roll toward it like a marble rolling toward the center of a stretched bedsheet, with a bowling ball in the middle. In 1916, just months after Einstein published his equations, a German physicist named Karl Schwarzschild solved them for a perfectly spherical mass. What he found was strange. There was a radius now called the Schwarzschild radius, where if you compressed enough mass into a small enough space, the curvature of space-time would become so extreme that nothing, not even light, could climb back out. The boundary at that radius became known as the event horizon. Cross it, and you've left the universe we know. You're still technically in space-time, but you're in a region where all paths, all futures, all possible directions lead only inward, only down, only toward the center, toward the singularity. the point where density becomes infinite and the mathematics we use to describe reality simply break down and weep. For decades, black holes remained theoretical. Beautiful, terrifying ideas written in the language of equations, but never seen, never touched, never proven. Then in 1964, astronomers detected powerful X-rays coming from a binary star system called Cygnus X1. One star was visible, a blue supergiant orbiting something invisible, something with at least 15 times the mass of the Sun, something that was pulling gas from the supergiant and heating it to millions of degrees as it spiraled inward, creating those X-rays like a scream in the electromagnetic spectrum. That invisible something was the first confirmed black hole. Since then, we've found dozens more, some close, relatively speaking, like the black hole in the system, HR 6819, discovered in 2020, sitting about 1,000 light-years away. Some unimaginably distant, like the supermassive black holes and quasars billions of light-years away so far that we're seeing them as they were when the universe was young, when galaxies were still forming, when time itself was just learning how to unfold. And here's what's quietly astonishing. Despite their reputation, despite the way they've become cosmic monsters in our imaginations, black holes don't actually suck. They're not vacuum cleaners. They're not hungry mouths devouring everything in their path. That's a misconception, one that's easy to fall into, but it's not quite accurate. A black hole's gravitational pull at a distance is no stronger than the pull of any other object with the same mass. If you replaced our sun right now in an instant with a black hole of exactly the same mass, something strange would happen. The sun would vanish. The sky would go dark. Earth would freeze. The oceans would turn to ice life as we know it would end. But our orbit wouldn't change at all. We'd keep circling that black hole at exactly the same distance, taking exactly 365 days to complete each frozen year, because the gravitational pull at Earth's orbital distance would be identical. A one solar mass black hole pulls exactly as hard as a one solar mass star, as long as you're far enough away. The danger isn't the pull. The danger is what happens when you get close, when you approach the event horizon. When the gradient of gravity, the difference in gravitational strength across short distances, becomes so steep that it can tear things apart atom by atom. But we're getting ahead of ourselves. Let's think about what a black hole actually is. Not just the mathematics, but the thing itself. Imagine you have a star, a big one burning through its fuel for millions of years. Hydrogen fusing into helium in its core, helium fusing into heavier elements, the star held in balance by the outward pressure of all that nuclear fire pushing against the inward crush of its own gravity. It's a war, and for most of a star's life, it's a tie. Pressure pushes out. Gravity pulls in. The star stays the same size. But eventually the fuel runs out. The core cools. The pressure drops. And gravity wins. The star collapses inward in a fraction of a second. And if it's massive enough, nothing can stop it. Neutron degeneracy pressure, which can hold up smaller dead stars, as neutron stars isn't enough. The atoms themselves are crushed. Electrons and protons merge into neutrons. Neutrons crush into something else, something we don't have a name for, something that might not be made of particles at all anymore. And it keeps collapsing until all that mass 2, 5, 10, 20 times, the mass of the sun is compressed into a region smaller than a city, smaller than a mountain, smaller than anything we can meaningfully visualize. That's a stellar mass black hole. And the boundary around it, the event horizon, might have a radius of just a few kilometers. For a 10 solar mass black hole, the Schwarzschild radius works out to about 30 kilometers. It seems as though that should be enormous, but in cosmic terms, it's nothing. A speck, a pinprick, a place where the universe has folded in on itself so completely that space and time trade places, and the direction forward in time becomes the direction inward toward the center. Scientists have observed black holes in binary systems pulling gas from companion stars. They have detected gravitational waves, ripples in space-time itself, created when black holes spiral into each other and merge events so violent they release more energy in a fraction of a second than all the stars in the observable universe combined. In 2019, the Event Horizon Telescope, a global network of radio observatories working together, captured the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy. M87, a giant 55 million light-years away, with a mass of 6.5 billion suns. The image showed a ring of light, glowing gas swirling around the black hole's event horizon, and in the center, a dark circle. Not because there's a physical surface there isn't, but because light from behind the black hole has been bent so severely by gravity that it wraps around in strange loops, and the region inside the event horizon emits nothing, reveals nothing, reflects nothing. It's a hole in the picture, a hole in space-time, a place where if you could somehow stand there and look around, you'd see the universe compressed into a bright ring above you and endless darkness below. But here's the question we're holding tonight. What if one of those objects, silent, invisible, patient, came wandering through our neighborhood? What if a black hole, maybe a stellar mass one, born from the death of a star millions of years ago, maybe something larger passed close to Earth, not close enough to touch, but close enough to matter? Would we see it coming? Would we feel it? Would there be time to prepare, to understand, to say goodbye? Or would it happen slowly over centuries, over millennia, as orbits shifted and tides grew, and the familiar rhythm of day and night began to change in ways too subtle to notice until it was far too late? You don't need to understand everything. Just rest and let curiosity do the listening. Because tonight we're going to walk slowly and gently through what would happen, not with panic, not with fear, but with the quiet attention of someone watching a storm roll in from miles away, knowing it's real, knowing it's coming, but also knowing that there's a kind of beauty in understanding how the pieces fit together, how gravity works, how space-time bends, how fragile and how resilient our little world actually is. And maybe we'll find that even in the thought of darkness passing close, there's something worth seeing, something worth knowing. The universe is vast. Black holes are scattered through it like seeds in soil, most of them far, far away, minding their own slow spiral through the galactic disk. But distance in space is a matter of time. And time, as we'll see, is one of the first things a black hole begins to change. So let's begin there. Let's begin with distance, with approach, with the slow, patient mathematics of gravity reaching out across the light years, touching our sun, touching our planet, touching us. Let's imagine a stellar mass black hole, perhaps 10 times the mass of the sun, dark and silent, drifting through the Milky Way. And let's imagine that its path by chance or by the slow clockwork of galactic orbits brings it toward us. Not tomorrow, not next year, but someday. In some version of reality. In some thought experiment written in starlight and shadow. Let's imagine it's coming, and let's see what happens when it arrives. A black hole is not a hole. That's the first thing to understand and maybe the hardest. The name misleads us. It suggests emptiness, a gap, a missing piece of space. But a black hole is the opposite of empty. Its matter compressed so densely that a teaspoon of it would weigh more than Mount Everest. It's not absence. Its presence taken to an extreme we can barely imagine. So, what exactly are we talking about when we talk about black holes? Let's build one slowly from the ground up. Imagine you're holding a ball, any ball, a baseball perhaps. Now imagine compressing it, squeezing it smaller and smaller, but keeping all its mass, every atom, every particle intact. As you compress it, its gravitational pull at the surface gets stronger. Not because there's more mass, but because you're getting closer to all of it. Gravity follows what's called an inverse square law. Double the distance, and gravity becomes 4 times weaker. Halve the distance, and it becomes 4 times stronger. Keep compressing. The ball becomes the size of a marble, then a grain of sand, then smaller still. At some point, and this point is different for every amount of mass, you reach a critical radius, the Schwarzschild radius, named after Karl Schwarzschild, who calculated it in 1916 while serving in the German army during World War I, solving Einstein's equations in the trenches between artillery barrages. The Schwarzschild radius is the distance from the center of a mass at which the escape velocity equals the speed of light. Escape velocity is the speed you'd need to break free of an object's gravity. On Earth, it's about 11 kilometers per second. On the Moon, it's much less. On Jupiter, much more. But for any mass compressed within its Schwarzschild radius, the escape velocity exceeds 300,000 kilometers per second, the speed of light itself. And since nothing can travel faster than light, scientists believe that nothing can escape. That boundary, the sphere at the Schwarzschild radius, is the event horizon. It's not a surface. There's nothing physical there. It's simply the point of no return, the place where the gravitational well becomes so steep that all future paths lead inward. For our sun, with its mass of roughly 2 × 10 to the power of 30 kilograms, the Schwarzschild radius works out to about 3 kilometers. If you could somehow compress the entire sun, all its light, all its heat, all its million-kilometer diameter, into a sphere just 6 kilometers across, you'd have a black hole. The Earth would still orbit at the same distance, feeling the same gravitational pull it always has because the mass hasn't changed. Only the density has. For Earth itself, the calculation is even stranger. Our planet would need to be compressed to about 9 millimeters, roughly the size of a peanut, to become a black hole. All the mountains and oceans and cities and clouds, all the iron core and molten mantle squeezed down until it could fit in your palm. It seems as though it should be impossible, and under ordinary circumstances, it is. Matter resists. Atomic forces push back. But in the collapsing core of a massive star where temperatures exceed billions of degrees and pressures overcome every force trying to hold things apart, the impossible becomes inevitable. There are different types of black holes classified by mass. Stellar mass black holes form from dying stars and typically range from about 3 to maybe 100 times the mass of the Sun. Research shows these are the most common type born in supernova explosions when stars at least 20 times the Sun's mass reach the end of their fusion cycles. The outer layers explode outward at tens of thousands of kilometers per second. The core collapses inward even faster. What's left is a black hole with a Schwarzschild radius of perhaps 10 to 300 kilometers small by cosmic standards, but gravitationally intense up close. Then there are supermassive black holes, the giants at the centers of galaxies. These range from hundreds of thousands to billions of solar masses. Our Milky Way's Sagittarius A star weighs in at about 4.3 million solar masses, with an event horizon roughly 17 times the diameter of the Sun. The supermassive black hole in M87, the first ever photographed, contains 6.5 billion solar masses. Its event horizon could swallow our entire solar system out to Neptune's orbit and still have room to spare. Scientists aren't entirely sure how supermassive black holes form. Some suggest they grow from stellar mass black holes that feast on surrounding gas and merge with other black holes over billions of years. Others propose they formed directly in the early universe, collapsing from massive clouds of primordial hydrogen before the first stars even ignited. The truth might be some combination of both. There's also speculation about intermediate mass black holes filling the gap between stellar and supermassive and primordial black holes, tiny ones that might have formed in the first fraction of a second after the Big Bang, when the universe was dense enough that quantum fluctuations could collapse into black holes smaller than atoms. These remain theoretical. We've never detected one, but if they exist, they could be anywhere, everywhere. invisible, undetectable except through their gravitational effects, drifting through space like cosmic ghosts. Here's a common mistake people make, assuming smaller black holes are less dangerous. Intuitively, it makes sense. A bigger black hole should be worse, right? But the opposite is true in one crucial way. The tidal forces, the difference in gravitational pull across an object, are actually stronger near smaller black holes. Imagine you're falling feet first toward a black hole. Your feet are closer to the center than your head, so they feel slightly more gravity. The smaller and denser the black hole, the steeper that gravitational gradient becomes over short distances. For a 10 solar mass black hole, the tidal force at the event horizon would be strong enough to stretch you into a thin stream of atoms long before you crossed it, a process called spaghettification, which sounds whimsical but is absolutely not. But for a supermassive black hole like Sagittarius A star, the event horizon is so far from the center that the tidal forces at that distance are actually quite gentle. Scientists have calculated that you could cross the event horizon of a 1 billion solar mass black hole and barely feel anything unusual. You'd notice nothing special in your immediate surroundings. You could look around, check your instruments, feel perfectly fine until you tried to turn around. Until you realized that every direction you could move, every path you could take, led deeper inward, and by then, it would be far too late. So, size matters, but not in the way we expect. The event horizon itself is strange to think about. It's not a boundary in space exactly. It's a boundary in space-time. Inside it, the rolls of time and space trade places. Outside a black hole, you can move freely through space, left, right, forward, back, but you're dragged inexorably forward through time. You can't stop time. You can't go backward. Time pulls you along, whether you like it or not. But inside the event horizon, scientists suggest that changes. The inward direction toward the singularity becomes as inevitable as moving forward in time. You can no more stop yourself from falling inward than you could stop yourself from aging. And the time direction becomes something you could in principle move through differently. Though the mathematics of exactly what that means makes even physicists' heads hurt. At the very center of a black hole sits the singularity, the point where all the mass is concentrated. Classical general relativity predicts that it's infinitely dense, a place where space-time curvature becomes infinite, and the equations produce infinities that make no physical sense. Most scientists believe this is a sign that general relativity breaks down at that scale, that we need a theory of quantum gravity to understand what really happens there. Maybe it's not a point at all. Maybe it's a region where space and time dissolve into something else, some quantum foam of possibilities we don't yet have the language to describe. But we're dancing around the edges of what we know and don't know. Let's come back to something more concrete. Black holes don't glow. They don't emit light. That's part of what makes them black. But they can be surrounded by glowing matter. When a black hole pulls gas from a nearby star, or drifts through a nebula, that gas doesn't fall straight in. It has angular momentum. It's moving sideways as well as inward, so it spirals down, forming a flat disk called an accretion disk. Friction between particles in the disk heats the gas to millions of degrees hot enough to emit X-rays, ultraviolet light, visible light. Some of the most luminous objects in the universe, quasars, are supermassive black holes surrounded by accretion disks, so bright they outshine entire galaxies. Some black holes also produce jets, narrow beams of particles and radiation blasted outward from the poles at nearly the speed of light, powered by magnetic fields twisted in the swirling gas. These jets can extend for thousands of light years, punching through intergalactic space like cosmic searchlights. But if a black hole is alone drifting through empty space far from any stars or gas clouds, it emits essentially nothing. No light, no heat, no radiation, except for an unimaginably faint glow called Hawking radiation. A quantum effect, predicted by Stephen Hawking in 1974, where particle pairs form at the event horizon and one falls in, while the other escapes, causing the black hole to very, very slowly evaporate over timescales trillions of times longer than the current age of the universe. A stellar mass black hole left alone would take something like 10 to the power of 67 years to evaporate completely. The universe is only about 14 billion years old, 10 to the power of 10 years. So, for all practical purposes, black holes are permanent. Once they form, they're here to stay. Which brings us back to the question at hand. If a black hole were wandering through the galaxy, heading in our general direction, how would we know? How would we detect it? If it's actively pulling gas from something nearby, we might see X-rays. We might notice a star wobbling, orbiting an invisible companion. That's how we found the first black hole candidates, by watching stars dance around nothing. But a solitary black hole, one that's been drifting alone for millions of years, wouldn't emit anything we could detect directly. We'd have to notice its gravitational effects. Maybe it would pass in front of a distant star and bend its light through gravitational lensing, creating a brief brightening or a distorted image. Maybe it would tug on the orbits of planets or comets at the edge of the solar system, creating perturbations we could measure if we were paying close enough attention. The closest known black hole to Earth, discovered in 2020, is the one in the HR 6819 system, about 1,000 light-years away. It orbits two visible stars in a triple system. We found it by watching one of those stars wobble, betraying the presence of something massive when invisible. 1,000 light-years sounds far, and it is. Light from that system takes a millennium to reach us. But in galactic terms, it's close. It's in our neighborhood. And if there's one black hole that closed, there are likely others we haven't found yet. Some estimates suggest there could be tens of millions of stellar mass black holes in the Milky Way, most of them wandering alone through the dark, undetected and undetectable, unless they happen to pass close to something that reveals them. It's a humbling thought. That darkness isn't empty. That the spaces between stars contain objects so dense and so strange that they warp the fabric of reality itself. And we only notice them when they happen to intersect with our line of sight or tug on something bright enough for us to measure. What would it take for one of them to come close to us? Not to hit us. That's so statistically unlikely it's not worth calculating, but to pass close enough to affect us. Gravity weakens with distance, but it never truly goes away. Even a black hole 10 light-years away would exert some tiny gravitational tug on the sun on Earth on you. Too small to measure, too small to matter, but present nonetheless. As it got closer, that tug would grow. At a certain distance, maybe a light-year, maybe closer, it would begin to influence the orbits of objects in the outer solar system. Comets in the Oort cloud would feel it first, their slow distant orbits shifting slightly. Then, objects in the Kuiper belt. Then, Neptune, Uranus, the outer planets. The details depend on the mass of the black hole, its velocity, its trajectory. But the principle is the same. Gravity reaches out across the void, patient and relentless, and when two massive objects come close, they change each other. They reshape each other's paths through space-time. And if a black hole came close enough, it wouldn't be subtle, it wouldn't be gentle, it would be the most profound encounter in Earth's history. But before we explore what that encounter would look like, before we walk through the consequences step by step, we need to understand one more thing about black holes. One more piece of their architecture, one more way they reshape not just space, but time itself. Distance in space is a kind of protection. It's not a wall, not a shield, just emptiness, vast and patient-keeping objects separated by gulfs so wide that even traveling at the speed of light, you'd spend years, centuries, millennia crossing them. The nearest star to our sun is Proxima Centauri, about 4.2 light-years away. Light leaving there right now won't reach Earth until 4 years from now. And between here and there, almost nothing. A few atoms per cubic meter, darkness, silence, space. But what happens when that distance begins to shrink? When something massive, something with 10 times the sun's mass compressed into a sphere, the size of a city starts drifting closer. Not quickly, not dramatically, just slowly, inevitably following whatever trajectory brought it into our region of the galaxy. How close would it need to come before we noticed? Before gravity reached across the void and touched us? Let's walk through it step by step, starting from far away and moving inward. Imagine our black hole at a distance of 1 light year from the solar system. That's about 63,000 astronomical units, 63,000 times the distance from Earth to the Sun. At that distance, the black hole's gravitational influence on Earth would be negligible, maybe 1/10,000,000th of the Sun's pull. You wouldn't feel it. Instruments wouldn't measure it. The planets would continue their orbits as if nothing had changed. But astronomers might notice something. If the black hole passed in front of a distant star, its gravity would bend the starlight in a phenomenon called gravitational microlensing. The star would appear to brighten for a few days or weeks, as the black hole's gravity acted like a lens, focusing more of the star's light toward Earth. Then it would fade back to normal as the black hole moved on. This technique has been used since the 1990s to detect dark objects, planets' brown dwarfs, even possibly black holes drifting through the galaxy. In 1993, astronomers began the MACHO project, Massive Compact Halo Objects, using microlensing to search for dark matter in the Milky Way's halo. They monitored millions of stars in the Large Magellanic Cloud, watching for the telltale brightening that would indicate something massive passing in front. They found events, lots of them. Most were probably ordinary stars too faint to see directly, or perhaps brown dwarfs, failed stars that never ignited fusion. But some events remain unexplained, and it's possible, just possible, that a few were caused by black holes drifting through the line of sight. So at 1 light year, we might detect the black hole through microlensing if we were paying attention and if it passed in front of the right star at the right time. But we wouldn't feel it. Not yet. As the black hole drifted closer, half a light year, then a quarter, its gravitational influence would grow. At half a light year, roughly 30,000 AU objects in the Oort cloud would begin to feel it. The Oort cloud is a vast spherical shell of icy bodies surrounding the solar system, extending from about 2,000 AU to as far as 100,000 AU from the Sun. It's where long-period comets come from chunks of ice and rock that occasionally get nudged inward by gravitational perturbations and fall toward the inner solar system, growing tails as they approach the Sun and heat up. A black hole passing through or near the Oort cloud would perturb thousands of these objects. Some would be pulled slightly inward, their orbits shortened, making them more likely to eventually fall sunward and become comets. Others would be flung outward, perhaps even ejected from the solar system, entirely sent on trajectories that would take them into interstellar space, never to return. Over months and years, Earth might experience an uptick in comet activity. More bright comets visible in the night sky. More impacts perhaps, as some of those perturbed objects happened to cross Earth's orbit at the wrong time. Astronomers tracking near-Earth objects would notice the increase and wonder what was causing it. They'd run simulations, calculate back trajectories, and eventually conclude that something massive had disturbed the Oort cloud. But identifying that object as a black hole would be difficult without direct observation. It could be a rogue planet, a brown dwarf, even an ordinary star on an unusual trajectory. The key would be looking for it, scanning the sky with infrared telescopes, searching for the heat signature that a normal star or planet would emit, and finding nothing. No infrared glow, no reflected light. Just a gravitational presence inferred from the motion of other objects. At a quarter light year, about 15,000 AU, the effects would escalate. The Kuiper Belt, the region beyond Neptune, where Pluto and thousands of other icy objects orbit, would begin to feel the black hole's pull. Orbits would shift. Resonances, the gravitational relationships between objects that keep their orbits stable, would break down. Some Kuiper Belt objects might be pulled into the inner solar system. Others might collide with each other, as their paths changed unpredictably. Neptune and Uranus, the outermost major planets, would show the first signs of orbital perturbation. Their positions predictable to within a few kilometers based on centuries of observation and Newtonian mechanics would begin to deviate. Not by much, maybe a few hundred kilometers at first, but enough for astronomers to notice. Ephemerides, the tables predicting planetary positions, would need correction. Something was pulling on the outer planets, and it wasn't accounted for in the models. By the time the black hole reached 50 AU, roughly the distance to Pluto at its farthest, the perturbations would be undeniable. Pluto's orbit would change visibly over the course of months. Neptune and Uranus would show measurable acceleration or deceleration, depending on where they were in their orbits relative to the black hole's trajectory. And by now, someone somewhere would have figured it out. The calculations would point to an object with about 10 solar masses moving at some velocity, maybe 20 or 30 kilometers per second, typical for stars in this region of the galaxy passing through the outer solar system. There would be debates, papers published, press conferences. Is it a black hole? Could it be something else? How close will it come? When will it reach perihelion, its closest approach to the sun? And most importantly, what will happen to Earth? Because by now, it would be clear that something was going to happen. The question was, how severe? As the black hole crossed 30 AU entering the region of Neptune's orbit, the gravitational dynamics would become complex. Neptune itself, with a mass of about 17 Earths, would interact with the black hole gravitationally. Depending on the geometry of the encounter, Neptune could be pulled into a more elliptical orbit, its distance from the Sun varying more than it currently does. Or it could be pulled outward, perhaps even ejected from the solar system entirely if the encounter were close enough and at the right angle. There's a historical precedent for thinking about such encounters, though not with black holes. In the 1990s, astronomers observed Jupiter interacting with comet Shoemaker-Levy 9. The comet had passed too close to Jupiter on a previous orbit and been torn apart by tidal forces, fragmenting into more than 20 pieces. In July of 1994, those fragments collided with Jupiter over the course of a week, creating dark impact scars visible through amateur telescopes and releasing energy equivalent to millions of megatons of TNT per impact. Jupiter survived, obviously. It's massive enough that even a comet impact is barely noticeable in the long term. But the event demonstrated how gravitational interactions can reshape objects, fragment them, change their trajectories irreversibly. A black hole interacting with Neptune wouldn't fragment the planet. Neptune is held together by its own gravity far more strongly than a comet. But it could change Neptune's orbit dramatically, and those changes would propagate inward, affecting Uranus, then Saturn, then Jupiter, each planet tugging on the next, through gravitational interactions that normally keep the solar system stable over billions of years. At 20 AU, roughly the distance to Uranus Earth would begin to feel the effects indirectly. Our orbit wouldn't change much, yet we're too far from the black hole for that. But the other planets' changing orbits would affect us through gravitational resonances. The solar system is a delicately balanced system. Planets don't just orbit the sun independently. They orbit each other in a complex gravitational dance with periods and distances that have settled into stable configurations over billions of years. Disturb one planet significantly, and the disturbance propagates. Jupiter, the most massive planet, normally acts as a gravitational shepherd, keeping smaller objects in check. But if Jupiter's orbit changes, if it's pulled slightly inward or outward by the black hole's passing, then its gravitational influence on Earth changes too. Earth's orbit might elongate slightly, or tilt, or precess in ways that affect our seasons and climate. At 10 AU, the distance to Saturn, the situation would become critical. Saturn is a giant about 95 times Earth's mass, but compared to a 10 solar mass black hole, it's insignificant. The black hole could pull Saturn into a highly elliptical orbit, or even capture it, pulling it away from its current orbit and sending it on a new trajectory that might intersect other planets' paths or eject it from the solar system entirely. And here's where things get interesting in a terrifying sort of way. Planets can act like gravity assists, like slingshots for other objects. When spacecraft fly by planets, they can steal a bit of the planet's orbital momentum and speed up a technique called a gravity assist, or gravitational slingshot. Voyager 2 used this technique to visit Jupiter, Saturn, Uranus, and Neptune in a single mission, each planet boosting it onward to the next. A black hole passing through the solar system could use planets as gravity assists too, though in reverse, taking energy from their orbits and changing their paths. Or the planets could deflect the black hole, changing its trajectory slightly, which might make the difference between the black hole passing relatively harmlessly through the outer system or plunging deeper inward toward Earth. At 5 AU Jupiter's distance, the effects on Earth would become direct and measurable. The black hole's gravity would start to compete with the sun's. Earth's orbit would no longer be determined primarily by the sun's pull. The black hole's pull would be significant too, perhaps 10 or 20% as strong depending on the exact positions. This is where orbital mechanics becomes less predictable. In a two-body system, Earth and Sun or Earth and Moon, orbits are stable and calculable. But add a third massive body, and the system becomes chaotic in the mathematical sense. Small changes in initial conditions lead to wildly different outcomes. This is the famous three-body problem unsolved in the general case, a source of frustration for astronomers and physicists for centuries. Henri Poincaré, the French mathematician, won a prize in 1889 for his work on the three-body problem, though his solution showed that exact long-term predictions were impossible. The system was deterministic, governed by precise laws, but unpredictable beyond a certain timescale because tiny uncertainties in initial conditions would amplify exponentially. With a black hole at 5, AU Earth would be in a three-body system, Sun-Earth black hole, and our orbit would become uncertain. Computer simulations could predict what might happen, but they'd have to account for enormous numbers of variables, the black hole's exact mass velocity trajectory, the positions of all the planets, their mutual gravitational interactions. Run the simulation twice with slightly different starting conditions, and you might get completely different outcomes. In one simulation, Earth's orbit elongates but remains stable. In another, Earth is pulled into a closer orbit around the Sun. In a third, Earth is ejected entirely sent, wandering through interstellar space as a rogue planet. At 3 AU, the uncertainty would resolve into certainty, but not the comforting kind. By now, the black hole's influence would dominate. Earth's orbit would be visibly changing, weeks shortening or lengthening as our distance from the sun varied. The climate would respond. Seasons would feel wrong. Scientists would issue warnings. Governments would make plans, though what plans could possibly help in such a scenario is unclear. And at 1 AU, the current distance from Earth to the Sun, if the black hole's trajectory brought it that close, Earth would be in immediate existential danger. Not from falling into the black hole necessarily. Even at 1 AU, the black hole is still 93 million miles away. But from orbital disruption, from tidal forces, from the cascading gravitational chaos that would ensue as the black hole plowed through the inner solar system, reshaping everything it touched. There's something quietly horrifying about the inevitability of it. Once the black hole is on a trajectory toward the inner system, there's nothing we could do to stop it. No technology we currently possess or can imagine possessing in the near future could deflect something with 10 times the sun's mass. We'd just have to watch it approach, calculate the probabilities, and wait to see which version of the future unfolded. But here's the thing worth remembering. Space is vast. The odds of such an encounter are vanishingly small. And even if a black hole were approaching, we'd likely have decades or centuries of warning, enough time to track it, study it, understand exactly what was coming. And in that understanding, even faced with something we couldn't prevent, there would be a kind of clarity, a final chance to see the universe as it actually is, not designed for our comfort, not arranged for our survival, but operating according to laws that we've learned to read, to predict, to comprehend. The black hole wouldn't care about us, but we would understand it, and maybe that's enough. Because understanding doesn't just tell us what's coming. It tells us what forces shape our world even when nothing catastrophic is happening. It tells us how stable our orbits are, how precisely balanced the solar system is, how much we depend on distances staying roughly constant and gravity behaving predictably. And as the black hole drew closer still, as its gravity reached out and began to reshape not just orbits, but the very structure of our planet, we learned something else. There's a gentleness to the tides we know. Twice a day the ocean rises, twice a day it falls. The rhythm is so familiar, so woven into coastal life, that we barely think about what causes it. But the tides are gravity made visible. They're the moon reaching across 240,000 miles of empty space and pulling on Earth's water, creating a bulge on the side facing the moon and another on the opposite side. The solid Earth itself rises and falls by about 30 centimeters. With each tide, we just don't notice because everything around us is moving together. The force creating those tides is called a tidal force, and it's one of the most important concepts for understanding what a black hole does when it comes near anything, including us. Tidal forces arise from the gradient of gravity, the difference in gravitational pull across an object. The moon pulls harder on the side of Earth facing it than on the side facing away. And that difference, small as it is enough to raise the oceans by a few meters. It's a gentle effect. Persistent, predictable, manageable. But when the source of gravity is dense enough, close enough, massive enough, tidal forces stop being gentle. They become violent, destructive, capable of tearing worlds apart. Let's imagine our black hole again. 10 solar masses, maybe a bit more. It's been drifting through interstellar space for millions of years, a silent wanderer born from some ancient star's death. And now, its trajectory is bringing it toward the inner solar system. It's still far away, let's say 50 astronomical units, roughly the distance to Pluto at its farthest point. Out here, its influence is subtle. Neptune and Uranus might feel a slight tug, a barely measurable change in their orbits. The Kuiper Belt objects, those icy remnants beyond Neptune, begin to shift some, pulled slightly inward, others nudge slightly outward. But Earth orbiting at 1 astronomical unit from the Sun feels almost nothing, not yet. As the black hole drifts closer, 40 AU, 30 AU, 20 AU, its gravitational influence grows. Not linearly, but according to that inverse square law. At 20 AU, it's pulling with 4 times the strength it did at 40 AU. At 10 AU, 16 times stronger. The outer planets feel it now. Jupiter's orbit begins to show perturbations. Saturn wobbles slightly. These are massive worlds, but compared to a 10 solar mass black hole, they're pebbles. At somewhere around 12 to 15 astronomical units, research suggests the gravitational disruption becomes severe enough that Earth's orbit starts to change noticeably. Not dramatically, not overnight, but over months and years, the shape of our path around the Sun would elongate or compress depending on the black hole's trajectory and speed. Our distance from the Sun would vary more than it should. Seasons would begin to feel wrong. Winters might last longer. Summers might feel shorter or hotter or colder depending on where Earth is in its now distorted orbit. At 10 astronomical units, roughly the distance from the Sun to Saturn, the tidal forces start to matter. Here's how tidal forces work. Imagine Earth as it is right now, a sphere about 12,700 kilometers in diameter. The side closest to the black hole feels slightly more gravitational pull than the center of the Earth. The side farthest from the black hole feels slightly less. This difference creates a stretching force along the line connecting Earth to the black hole and a compressing force perpendicular to that line. Earth gets pulled into a slightly elongated shape like an egg. with the long axis pointing toward the black hole. At 10 AU with a 10 solar mass black hole, the tidal force is still relatively small, maybe not even enough to notice in daily life. The oceans might show unusual tides higher than normal, unpredictable. Sensitive instruments might detect stress in Earth's crust, but nothing catastrophic, not yet. As the black hole moves closer, 8 AU, 6 AU, 5 AU, the tidal forces escalate. The oceans don't just rise higher, they start to respond chaotically. High tide might last for hours longer than it should. Coastal areas flood. Low-lying islands disappear. The gravitational gradient across Earth becomes steep enough that the solid crust itself begins to flex and bulge more than it ever has under the moon's influence. Scientists have studied tidal disruption events in astronomical observations. Stars that wander too close to supermassive black holes and get torn apart. In 1992, astronomers observed an event in a distant galaxy where a star was shredded by tidal forces, creating a bright flare as the star's gas spiraled into the black hole's accretion disk. The process is called spaghettification, a term coined by Stephen Hawking to describe what happens when the tidal gradient becomes so steep that an object is stretched into a long, thin strand. For a star, this happens relatively close to the black hole, within a few times the Schwarzschild radius. For a star approaching a supermassive black hole, research shows this might occur at distances of several million kilometers from the event horizon. For smaller, denser stellar mass black holes, the tidal forces become extreme even closer in. But planets aren't held together the same way stars are. Stars are balls of gas held together by their own gravity. Planets have solid or liquid layers with internal structure and varying densities. Rock, metal, water, ice. Earth has a molten iron core, a solid mantle, a thin crust ocean's atmosphere. Each layer responds differently to tidal stress. At around 5 astronomical units, scientists suggest Earth would begin to experience tidal heating. The constant flexing and stretching of the planet's interior from the changing tidal forces would generate heat through friction, the same way bending a paperclip back and forth makes it warm. This is the same mechanism that keeps Jupiter's moon Europa geologically active despite being so far from the sun. Europa's ice-covered surface hides a liquid ocean beneath, kept warm by tidal heating from Jupiter's gravity and the gravitational tugs of the other moons. For Earth, tidal heating from a passing black hole would manifest first as increased volcanic activity. Dormant volcanoes might wake, new fissures might open in the crust. Earthquakes would become more frequent and more severe as the planet's crust buckles under the stress. The tectonic plates, which normally move a few centimeters per year, might shift suddenly unpredictably. At 3 to 4 astronomical units, the moon would be at risk. The moon orbits Earth at a distance of about 384,000 kilometers, roughly 1/400th of an AU. The tidal forces pulling on the moon from the black hole would begin to compete with Earth's gravity, holding it in orbit. The moon's orbit would become unstable. It might spiral outward, breaking free from Earth entirely and becoming an independent object orbiting the sun or orbiting the black hole. Or it might spiral inward, pulled toward Earth in a slow-motion collision that would take months or years, but would be utterly unstoppable. Losing the moon would be catastrophic in ways that might not be obvious at first. The moon stabilizes Earth's axial tilt, keeping our seasons predictable. Without it, Earth's tilt would wobble chaotically over thousands of years, making long-term climate patterns impossible. The moon also creates tides that help circulate ocean currents and nutrients. Without those tides, ocean ecosystems would collapse. And the moon slows Earth's rotation through tidal friction over billions of years. It's lengthened our day from about 6 hours to 24. Without it, that process would reverse. Earth might begin spinning faster again, driven by other gravitational interactions, shortening our days unpredictably. But all of that becomes academic if the black hole comes closer still. At 2 astronomical units, Earth's crust would begin to crack. The tidal bulge, the elongation of the planet along the axis pointing toward the black hole, would be so pronounced that the solid rock itself couldn't hold together. Fissures would open, magma would pour out, the surface would heave and buckle like water in a storm. Research suggests that the tidal force differential across Earth's diameter at this distance would be strong enough to overcome the structural integrity of rock, especially in areas already weakened by fault lines or volcanic activity. Picture the mid-Atlantic ridge, where tectonic plates are slowly spreading apart, opening up at about 2 centimeters per year. Under extreme tidal stress, that spreading could accelerate to meters per day. The ridge would gape open. Seawater would pour into the gap, flash into steam from the heat of exposed magma, creating clouds of superheated vapor that would rise into the atmosphere and alter the climate within days. At 1 astronomical unit, the distance Earth normally orbits the Sun, a 10 solar mass black hole would exert a tidal force across Earth's diameter strong enough to literally tear the planet apart. The tidal acceleration, the difference in gravitational acceleration between near and far sides, would exceed Earth's own surface gravity. The side facing the black hole would be pulled away from the core faster than the core could hold it. The far side would lag behind. In between, the planet would stretch deformed fragment. This wouldn't happen instantly. It's not like snapping a stick. It would take hours, maybe days as the stress is built up. And the planet's internal structure failed piece by piece. First, the crust fracturing into massive sections. Then the mantle pulling apart like taffy. The core, initially resistant, would eventually succumb as well, fragmenting into chunks of molten iron and nickel. What's left wouldn't be a planet anymore. It would be a stream of debris, rock, metal, water. Ice stretching out along the orbital path, gradually spreading into a thin ring as different pieces moved at slightly different speeds. Some of this debris would fall toward the black hole, spiraling inward, heating up from friction and compression, eventually crossing the event horizon and disappearing. Some would be flung outward, escaping the system entirely doomed to wander the galaxy as orphaned fragments of a world that used to be. This kind of destruction has been observed at least indirectly. In 2010, astronomers using the Chandra X-ray Observatory and other telescopes observed a massive flare from a galaxy 470 million light-years away. The flare lasted for weeks, and analysis suggested it was a star being tidally disrupted by the supermassive black hole at the galaxy's center. The star was torn apart, and its gas formed a temporary accretion disk that glowed brightly in X-rays before eventually fading. Similar events have been detected dozens of times since then. Some show distinctive patterns in their light curves, the way brightness changes over time, that reveal details about how the disruption happened. Was the star disrupted from the side or head-on? Was it a dense star or a puffy one? How massive was the black hole? These observations give scientists a way to test their models of tidal forces in the most extreme conditions nature can produce. But here's something crucial to understand. The tidal force depends not just on the mass of the black hole, but on its size, specifically on the compactness of that mass. A supermassive black hole with 1 billion solar masses has such a large event horizon that the tidal forces at the horizon itself are actually quite gentle. You could, in theory, cross the event horizon of 1 billion solar mass black hole and feel essentially nothing unusual. The gradient of gravity would be shallow enough that the difference in pull between your head and your feet would be less than Earth's surface gravity. But a stellar mass black hole with 10 solar masses is much, much smaller. Its event horizon has a radius of only about 30 kilometers. The tidal forces near it are brutal. You'd be spaghettified long before reaching the event. Horizon stretched into a stream of atoms ripped apart at the molecular level, turned into something that resembles a strand of cosmic noodles more than anything that was ever alive. This is why counterintuitively smaller black holes are more dangerous up close. A supermassive black hole might pull you in, gently at least initially. A stellar mass black hole would shred you. For Earth caught between a 10-solar mass black hole and the Sun, the question becomes, at what distance do the tidal forces from the black hole exceed Earth's ability to hold itself together? The answer depends on something called the Roche limit, named after the French astronomer Edouard Roche, who calculated it in 1848. The Roche limit is the distance at which tidal forces from a massive body exceed the gravitational self-attraction of a smaller body. Inside the Roche limit, the smaller body breaks apart. Outside it, it stays whole. For Earth and a 10-solar mass black hole, the Roche limit is somewhere around 1 to 2 astronomical units, depending on Earth's internal structure and density. That's closer than Mars, but farther than Venus. If the black hole passed through that region, if its trajectory brought it within that critical distance, Earth would not survive intact. But even if the black hole never came quite that close, even if it passed at say 5 or 10 AU, the damage would be profound. The tides alone would reshape coastlines, trigger earthquakes, awaken volcanoes. The moon would likely be lost. Earth's orbit would be altered, perhaps permanently changing our distance from the sun, and making life as we know it impossible. And that's just the beginning of what would happen, because tidal forces are only one piece of the puzzle. There are other effects, other consequences, other ways a black hole's presence would remake our world. The fabric of space-time itself would ripple and flex. Time would flow differently in different places. Light would bend in strange ways. Gravity, it turns out, doesn't just pull, it transforms. Time doesn't flow the same way everywhere. That's one of the strangest truths Einstein's relativity revealed, and it's one of the hardest to accept. We experience time as universal as uniform, 1 second per second, everywhere, always. But that's an illusion created by living in a relatively weak gravitational field, moving at relatively slow speeds. Time is flexible, malleable, and near a black hole, it becomes something almost unrecognizable. If you've ever wondered what it would feel like to watch time slow down, to see the universe age around you, while you remain frozen in a moment, a black hole is where that stops being science fiction and becomes physics. Let's start with something we can measure right here, right now. At the top of Mount Everest, time passes slightly faster than it does at sea level. Not by much, we're talking about a few nanoseconds per day, but it's measurable with atomic clocks. In 2010, researchers at the National Institute of Standards and Technology in Boulder, Colorado, demonstrated this with remarkable precision. They used 2 atomic clocks identical in design, separated by just 33 centimeters vertically. The higher clock ran faster than the lower one by about 90 billionths of a second per day. Why? Because gravity affects time. The stronger the gravitational field, the slower time flows. This phenomenon is called gravitational time dilation, and it's not some minor correction or theoretical curiosity. It's essential to how GPS satellites work. The satellites orbit at about 20,000 kilometers above Earth's surface, where gravity is weaker than at ground level. Their onboard clocks run about 45 microseconds faster per day than clocks on Earth. If engineers didn't account for this, GPS coordinates would drift by about 10 kilometers per day. Your phone's map would become useless within hours. Einstein predicted this in 1915 with his general theory of relativity. He showed that massive objects don't just pull on other objects, they curve space-time itself. And in curved space-time, clocks tick at different rates, depending on how deep they are in the gravitational well. Near a black hole, this effect becomes extreme. Imagine 2 astronauts' twins, perhaps, to make the comparison clearer. One stays aboard a spacecraft orbiting far from a black hole safely distant. The other takes a smaller ship and descends closer, moving into a tighter orbit just outside the event horizon. They synchronize their watches before separating. They plan to reunite after 6 hours as measured by the distant astronaut's clock. 6 hours pass on the distant spacecraft. The astronaut looks out the window, waiting for her twin to return. And eventually she sees the ship climbing back up from the black hole's vicinity. They dock. She opens the airlock, eager to compare notes. Her twin steps out, checks his watch. Only 5 hours and 24 minutes have passed for him. He's 36 minutes younger than his sister, now despite being the same age when they separated. This isn't speculation. NASA astrophysicist Jeremy Schnittman calculated this exact scenario in 2024 as part of a simulation exploring what would happen near a supermassive black hole with 4.3 million solar masses, the same mass as Sagittarius A star, the black hole at the center of our galaxy. The numbers are precise. 6 hours far away equals 5 hours and 24 minutes close in. Time literally runs slower the deeper you sink into the gravitational well. And that's for a relatively gentle orbit one, where the astronaut never crosses the event horizon and manages to escape back to safety. If the black hole were rotating rapidly like the one depicted in the 2014 film Interstellar, which had physicist Kip Thorne as a scientific consultant, the time dilation could be far more extreme. In the movie, the characters visit a planet orbiting close to a rotating black hole and spend just a few hours on the surface. When they return to their ship, they find that 23 years have passed for the crew member who stayed behind. That's dramatized, but the physics behind it is sound. Near a rapidly rotating black hole, scientists believe time dilation could easily produce ratios of hundreds or even thousands to 1. But here's where it gets stranger. This time, dilation isn't just something the astronauts experience differently. It's real. It's physical. The distant astronaut actually ages more. Her cells divide more times. Her heart beats more often. If they had brought identical plants or animals, the ones on the distant ship would grow older, while the ones taken close to the black hole would remain younger. Time isn't an abstract dimension. It's woven into the structure of reality, and gravity pulls on it just as surely as it pulls on matter. Now, let's bring this back to Earth, back to our scenario of a 10 solar mass black hole drifting through the solar system. At 10 AU, the time dilation effect on Earth would be negligible, maybe a few nanoseconds per year difference between clocks on Earth and clocks far from both the sun and the black hole. You wouldn't notice it in daily life, but it would be there measurable real. As the black hole came closer, 5 AU, 3 AU, 1 AU, the effect would grow. Clocks on the side of Earth facing the black hole would run slightly slower than clocks on the far side. The difference would be tiny, perhaps microseconds per day, but scientists with sensitive enough instruments could detect it. Atomic clocks in laboratories would show desynchronization. GPS satellites would need constant recalibration. Precision experiments relying on exact timing would fail in unpredictable ways. If someone were standing on the surface of Earth at the point closest to the black hole, and someone else were on the opposite side of the planet, the person closer would age infinitesimally slower. Over a year, the difference might be a few milliseconds. Not enough to feel, not enough to see, but enough to measure. Enough to prove that time itself was being warped by the black hole's presence. This is fundamentally different from the time dilation caused by velocity, what's called special relativistic time dilation. If you travel at high speed, you age slower relative to someone standing still. But that's symmetric in a certain sense. From your perspective, the person standing still is the one who's moving and you see their clock running slow. It's only when you turn around and come back that the asymmetry reveals itself and you find you've aged less. Gravitational time dilation isn't symmetric, it's hierarchical. The deeper you are in a gravitational well, the slower your time runs, period. Everyone agrees on who's aging slower. There's no perspective where it reverses. Near a black hole's event horizon, the effect becomes so pronounced that it creates one of the most disturbing predictions of general relativity. Imagine you're watching someone fall into a black hole. You're far away safe, observing through a telescope. You see your friend in their spacesuit falling feet first toward the event horizon. As they get closer, something strange happens. They appear to slow down. Their movements become sluggish. The light from their suit shifts toward red, what's called gravitational redshift, a consequence of light climbing out of the deepening gravitational well and losing energy in the process. Your friend raises their hand to wave goodbye. From your perspective, that wave takes longer and longer to complete. Seconds stretch into minutes, minutes into hours. The light from their suit becomes dimmer, redder, fainter. They appear to freeze in place just above the event horizon, their image dimming until they fade from view entirely, the light too redshifted and too faint to detect anymore. From your perspective, they never cross the event horizon. They're stuck there forever, asymptotically approaching, but never quite reaching that boundary, their time slowing towards zero as they sink toward the place where escape velocity equals the speed of light. But from your friend's perspective, they feel nothing unusual. They fall through the event horizon smoothly, continuously. Their watch keeps ticking at exactly 1 second per second as it always has. They cross the boundary in finite time, maybe seconds, maybe minutes, depending on the black hole's mass. And once they're inside, they keep falling deeper and deeper until the tidal forces tear them apart, or they reach the singularity at the center. This is one of the most profound paradoxes in general relativity. Two observers experiencing the same event see it unfold in completely incompatible ways. From outside, the person never crosses. From inside, they cross smoothly. Both perspectives are valid. Both are true. Reality itself depends on where you're standing. It's not that time is an illusion. It's that time is local. Each observer has their own experience of duration, their own flow of moments, and there's no universal clock that everyone agrees on once gravity gets strong enough. Astronomers see this effect in real observations. When matter falls into a black hole's accretion, disk gas pulled from a nearby star. For instance, the light from that gas shifts to longer wavelengths as it sinks deeper. Research shows that gas orbiting close to the event horizon emits light that's significantly redshifted compared to gas farther out. This creates a characteristic signature in the spectrum of light we detect, and it's one of the ways scientists confirm that the object at the center is actually a black hole and not something else like a neutron star. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves ripples in space-time itself from two black holes spiraling into each other and merging. The signal lasted about 0.2 of a second and showed the black holes orbiting faster and faster as they approached their velocity, reaching a significant fraction of the speed of light just before they collided. The gravitational waves themselves carried information about how space-time was oscillating during that merger, and analyzing them allowed physicists to measure the masses and spins of the black holes with remarkable precision. What was striking about that event was the confirmation that black holes don't just distort space, they distort time in ways that propagate outward as waves. When LIGO's detectors registered those waves, they were measuring space-time itself, stretching and compressing by a distance smaller than the width of a proton. For a brief moment, the distance between the mirrors and the detector changed by an amount so tiny, it's almost incomprehensible, but it was enough. Enough to prove that space-time is dynamic, flexible, responsive to mass and energy and motion. If a black hole passed through our solar system, we wouldn't just experience tidal forces and orbital disruptions. We'd experience a distortion of time itself. And if the black hole's trajectory brought it very close to Earth, closer than a few AU, the time dilation effects would start to become noticeable in strange, subtle ways. Imagine satellite signals suddenly showing timing errors that make no sense. Communication delays that shouldn't exist. Clocks on Earth falling out of sync with clocks on the International Space Station in ways that couldn't be explained by the usual relativistic corrections. Astronomers trying to coordinate observations would find their timestamps mismatched. Radio telescopes listening for pulsars rapidly spinning neutron stars that emit regular pulses of radio waves. Nature's most precise clocks would detect pulses arriving off schedule not because the pulsars changed, but because the time between emission and detection had been warped by the black hole's passage. If someone were in a spacecraft between Earth and the black hole trying to maintain communication with both, they'd experience a kind of temporal isolation. Messages sent to Earth would seem to arrive delayed from the spacecraft's perspective, and messages from Earth would seem delayed in the opposite way. It would feel as though they were watching two different timelines, two different flows of history running at slightly different rates, unable to synchronize. This is what makes black holes so fundamentally alien. They don't just threaten to destroy matter. They threaten to break causality itself, the orderly flow of cause and effect that underlies everything we understand about how the universe works. Near a black hole, the past doesn't always stay in the past, and the future doesn't always wait politely for the present to finish. And yet, all of this is still happening outside the event horizon, outside the point of no return. Once something crosses that boundary, the strangeness escalates beyond anything we can easily describe. Inside the event horizon, scientists believe the roles of space and time exchange. The inward direction toward the singularity becomes as inevitable as moving forward in time. You can no more stop yourself from falling toward the center than you could stop yourself from aging. All possible paths, all possible futures converge on the same endpoint. The singularity awaits patient and inescapable at the end of every road. Some physicists speculate about what might exist beyond the classical description. Maybe quantum effects near the singularity prevent true infinite density. Maybe space-time breaks down into discrete chunks at the Planck scale, and the singularity is replaced by something finite, something strange, something we don't yet have the mathematics to describe. Maybe black holes are tunnels to other regions of space-time or other universes entirely, though there's no evidence for this and plenty of reasons to doubt it. But whatever the truth is, one thing seems clear: time, as we experience it, as we rely on it, as we assume it to be universal and absolute, is not fundamental. It's emergent contextual, shaped by mass and energy and motion. A black hole doesn't just warp space. It warps the very fabric of when. If a black hole passed near Earth, we wouldn't just lose our place in space. We'd lose our place in time as well. The steady rhythm of seconds and minutes and hours that governs everything from heartbeats to harvest seasons would become uncertain variable dependent on where you were standing and how close the darkness had come. And while time fractured and bent around us, while clocks disagreed and satellites fell silent, there would be other changes unfolding. Changes to the Earth itself, changes deep beneath the surface where the planet's molten heart responds to forces we rarely think about. Beneath your feet, right now, the Earth is moving. The crust floats on a layer of semi-molten rock called the mantle, which churns and flows in slow convection currents driven by heat from the planet's core. Tectonic plates drift across the surface at about the same speed. Your fingernails grow a few centimeters per year. Volcanoes breathe. Fault lines shift. Mountains rise grain by grain, while erosion wears them down just as slowly. It's all happening in geological time, measured in millennia and epochs. We barely notice it. We live our entire lives on what feels like solid, stable ground. But that stability is more fragile than we like to think. And if a black hole passed close enough, the ground beneath us wouldn't just shift, it would convulse. The Earth's interior is a layered system, each layer with its own density, composition, and behavior. At the very center sits the inner core, a solid sphere of iron and nickel, about 1,200 kilometers in radius, with temperatures reaching roughly 5,000 degrees Celsius, as hot as the surface of the sun. Surrounding that is the outer core, a liquid layer of molten iron about 2,000 kilometers thick, swirling in complex patterns that generate Earth's magnetic field through a process called the geodynamo. Above the core is the mantle about 2,900 kilometers thick, made of hot, dense rock that's technically solid, but flows over geological timescales like thick honey. And at the very top is the crust, the thin shell we live on, only about 30 to 50 kilometers thick under continents, and as thin as 5 to 10 kilometers under the oceans. If Earth were an apple, the crust would be thinner than the skin. This layered structure responds to forces. The moon's gravity creates tidal bulges in the solid Earth itself, not just the oceans raising and lowering the ground by about 30 centimeters twice a day. We don't feel it because everything around us moves together. But sensitive instruments can measure it. GPS stations detect the vertical motion. Seismometers record the slight changes in ground level. Now, imagine a gravitational force hundreds or thousands of times stronger than the moon's, depending on how close the black hole came. Imagine that force varying not just with the daily rhythm of tides, but changing unpredictably as the black hole's trajectory carried it through the solar system, pulling from different directions at different strengths, sometimes increasing over days, sometimes over hours. The mantle would respond first. Deep beneath the surface in regions where rock already flows slowly under pressure and heat, the changing tidal forces would accelerate that flow. Convection currents that normally take millions of years to complete a cycle might speed up driven by the additional stress. Hot material from deeper layers would rise faster. Cooler material would sink more rapidly. The mantle would churn like water coming to a boil. This process has an analog we can observe right now on Jupiter's moon Europa. Europa is slightly smaller than Earth's moon, with a surface covered in ice that's constantly being fractured and refrozen. Beneath that ice, research suggests lies a global ocean of liquid water, kept warm, not by sunlight. Europa is too far from the sun for that, but by tidal heating. Jupiter's enormous gravity combined with gravitational tugs from Europa's sister moons. Io and Ganymede flexes Europa's interior continuously. That flexing generates heat through friction enough to keep an ocean liquid despite being in the frozen outer solar system. In 2011, NASA scientists analyzed data from the Galileo spacecraft and estimated that Europa's interior generates about 2 trillion watts of heat from tidal forces alone. That's roughly equivalent to twice the total energy consumption of all human civilization at the time. And Europa is just a moon subjected to the relatively gentle tides from Jupiter at a distance of about 670,000 kilometers. For Earth experiencing tidal forces from a black hole at 5 or 10 AU, the heating would be far more intense. The planet's interior would begin to generate excess heat, not enough to melt the crust immediately, but enough to raise temperatures throughout the mantle by tens or even hundreds of degrees over months or years. Rock that was already close to its melting point in the upper mantle and regions beneath volcanic arcs and mid-ocean ridges would begin to melt more extensively. Magma chambers would fill faster than they could empty. Pressure would build, and eventually that pressure would find release. Volcanoes that had been dormant for centuries would wake, not all at once but gradually, unpredictably, as different magma chambers reach critical pressure at different times. Mount Vesuvius, which last erupted in 1944, might rumble back to life. Mount Rainier in Washington state, which last had a major eruption about 500 years ago, could experience a new eruptive phase. The Yellowstone caldera, which hasn't had a major eruption in about 640,000 years, might show signs of unrest, increased seismicity ground, deformation, changes in the temperature and chemistry of geothermal features. The historical record shows what happens when multiple volcanoes erupt in a short time span. In 1815, Mount Tambora in Indonesia erupted with such violence that it ejected roughly 160 cubic kilometers of material into the atmosphere, creating a volcanic winter that caused global temperatures to drop by about half a degree Celsius. The year 1816 became known as the year without a summer. Crops failed across Europe and North America. Snow fell in June in New England. Famine spread. It was the eruption of a single volcano, and it disrupted human civilization for years. Now imagine not one volcano, but dozens erupting within a few years of each other as tidal heating destabilized magma chambers worldwide. The ash and sulfur dioxide pumped into the stratosphere would create a veil that dimmed. Sunlight cooled the surface, disrupted weather patterns. The effects wouldn't be as sudden as a tidal disruption tearing the planet apart, but they'd be devastating in a slower, more insidious way. Earthquakes would become more frequent and more severe. Earth's crust is divided into major tectonic plates that grind past each other, collide, or pull apart along boundaries marked by fault lines. Most of the time, these movements are slow and smooth, accommodated by gradual deformation of the rock. But sometimes stress builds up faster than it can be released, and the rock fractures, suddenly snapping into a new configuration. That sudden release is an earthquake. The strongest earthquake ever recorded, the 1960 Chile earthquake, had a magnitude of 9.5 and released energy equivalent to about 178 gigatons of TNT, more than 3,000 times the energy of the atomic bomb dropped on Hiroshima. It ruptured a fault line roughly 1,000 kilometers long and caused tsunamis that reached as far as Japan and the Philippines. The ground displacement in some areas exceeded 20 meters. That earthquake was driven by the slow, steady convergence of the Nazca Plate beneath the South American Plate, a process that had been building stress for centuries. But if tidal forces from a black hole were adding additional stress to fault lines, worldwide earthquakes of that magnitude could become more common. The San Andreas Fault in California, the North Anatolian Fault in Turkey, the Cascadia subduction zone off the coast of the Pacific Northwest. All of these could rupture within months or years of each other, each releasing decades or centuries of accumulated stress in a matter of seconds. The Ring of Fire, the arc of volcanic and seismic activity that encircles the Pacific Ocean, would become even more active. Subduction zones, places where one tectonic plate slides beneath another, would experience accelerated movement. In some areas, the overriding plate might be pushed upward, raising coastal regions and creating new land. In others, it might subside, causing coastal areas to sink below sea level and be inundated by the ocean. Consider the 2011 Tohoku earthquake in Japan, which had a magnitude of 9.1 and triggered a tsunami that reached heights of up to 40 meters in some locations. The tsunami caused the Fukushima Daiichi nuclear disaster, released radioactive material into the environment, and led to the evacuation of hundreds of thousands of people. That earthquake shifted the main island of Honshu roughly 2.4 meters to the east, and caused parts of the seafloor to rise by several meters. If a black hole's tidal forces were inducing similar stress worldwide, the cumulative effect would be catastrophic. Coastal cities would face repeated tsunami warnings. Infrastructure designed to withstand earthquakes under normal conditions might fail under the increased frequency and intensity of seismic events. Dams could crack, buildings could collapse, underground pipelines carrying water, gas, and oil could rupture. And then there's the question of what happens to Earth's orbit itself. We've talked about tidal forces acting on the planet's structure, but those same forces also affect Earth's trajectory through space. A black hole passing at 5 AU wouldn't just pull on Earth, it would tug on our orbit, stretching it, compressing it, or tilting it, depending on the geometry of the encounter. Earth's orbit around the Sun is currently nearly circular, with an eccentricity of about 0.017. That means the distance from the Sun varies by only about 5 million kilometers over the course of a year, from about 147 million kilometers at perihelion in early January to about 152 million kilometers at aphelion in early July. That small variation contributes to seasonal differences, but it's not the main driver of seasons. The tilt of Earth's axis, about 23.5 degrees, is far more important. But if a black hole's gravity perturbed our orbit, the eccentricity could increase significantly. Earth might find itself swinging much closer to the Sun at perihelion and much farther away at aphelion. The temperature difference between the two extremes would become pronounced. Summers in one hemisphere might become scorching, with temperatures soaring above anything we've experienced in recorded history. Winters might plunge into deep cold with ice advancing from the poles. Alternatively, if the perturbation changed Earth's orbital radius without changing its shape much, we could end up in a more distant orbit farther from the Sun on average. Even a change of just a few percent would be enough to tip the planet into a prolonged ice age. Glaciers would advance, sea levels would drop as water became locked in ice sheets. Ecosystems adapted to current temperatures would collapse, or we could end up closer to the Sun with global temperatures rising. Ice caps would melt. Sea levels would rise by tens of meters, drowning coastal cities. Weather patterns would shift as the increased energy in the atmosphere drove more intense storms, more severe droughts, more extreme rainfall. Some scientists have studied past orbital variations as part of Milankovitch cycles, changes in Earth's orbit and axial tilt that occur over tens of thousands of years and are thought to drive the Ice Age cycles of the Pleistocene epoch. These cycles involve relatively small changes, variations in eccentricity precession of the axis changes in the tilt angle. But even those small changes occurring over millennia have been enough to repeatedly plunge Earth into ice ages and then lift it out again. A sudden perturbation from a black hole wouldn't give ecosystems millennia to adapt. It would happen over years or decades. Species wouldn't have time to migrate to more suitable climates. Food chains would collapse. Agriculture, which depends on predictable seasonal patterns, would fail. And there's one more subtle effect worth mentioning. Earth's rotation itself could be affected. Currently, Earth spins on its axis once every 24 hours, and that spin rate is gradually slowing due to tidal friction with the Moon about 2 milliseconds per century. But if the Moon were lost, either ejected from orbit or pulled into a collision with Earth by the black hole's tidal forces, that tidal braking would disappear. Earth's rotation might begin to speed up again, driven by other gravitational interactions and the redistribution of mass as the planet's shape changed. A faster rotation would shorten the length of a day. It might seem like a minor issue, but biology is attuned to the 24-hour day. Circadian rhythms in humans, animals, and plants are calibrated to that cycle. A 19 or 20-hour day would disrupt sleep patterns, reproductive cycles, migration timing. It would be yet another stressor on ecosystems already struggling to cope with changing climates and geological upheaval. The geological consequences of a black hole's passage wouldn't be as immediate or as visually dramatic as the planet being torn apart by tidal forces, but they'd be profound. They'd unfold over months and years, a slow-motion disaster that reshaped continents, altered coastlines, and made the solid ground we depend on feel suddenly terrifyingly unreliable. And while the Earth shook and the mantle churned and the crust fractured, there would be something else changing, something we might not notice at first in the chaos, something in the sky, something in the way light itself behaves when space-time warps around a black hole. Light doesn't always travel in straight lines. We think it does. We build our understanding of the universe on that assumption. Look up at a star, and you assume the light reaching your eye left that star and traveled directly to you across the intervening space, undeflected, unchanged. But that's only true when space-time is flat, and near a massive object, a planet, a star, a galaxy, a black hole, space-time curves. And when space-time curves, light follows that curve. If a black hole passed close to Earth, the sky itself would transform. Stars would shift from their familiar positions. Constellations would warp and distort. The darkness wouldn't just pull on matter. It would pull on light itself, bending it, twisting it, creating illusions and revelations in equal measure. The bending of light by gravity is called gravitational lensing, and it was one of the first predictions of Einstein's general relativity to be tested observationally. In May of 1919, during a total solar eclipse, British astronomer Arthur Eddington led expeditions to Principian Island off the coast of West Africa and to Sobral in Brazil. Their goal was to photograph stars near the sun during the eclipse when the sun's glare wouldn't overwhelm the starlight, and measure whether those stars shifted from their normal positions. They found that stars near the sun's edge in the sky appeared displaced by about 1.75 arc seconds, roughly 1/2000th of a degree, exactly as Einstein's equations predicted. The sun's mass was bending the starlight passing near it, causing the stars to appear slightly farther from the sun than they actually were. When the results were announced in November of that year, it made headlines worldwide. Einstein became a celebrity overnight. General relativity was confirmed. Since then, gravitational lensing has become one of the most powerful tools in astronomy. Massive galaxy clusters lens light from more distant galaxies behind them, creating arcs rings and multiple images of the same object. In some cases, the lensing is so strong that it magnifies the background object, allowing astronomers to see galaxies that would otherwise be too faint to detect. In 2012, the Hubble Space Telescope captured an image of a galaxy cluster called MAX J0416.1-2403, which acted as a gravitational lens to reveal some of the most distant galaxies ever observed, galaxies whose light had been traveling for over 13 billion years. The cluster's gravity bent and amplified that ancient light, turning the cluster into a natural telescope far more powerful than Hubble alone. Black holes create the most extreme gravitational lensing in the universe. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy. M8755 million light-years away, the image showed a bright ring of light surrounding a dark central region. That bright ring wasn't the black hole itself. It was light from hot gas in the accretion disk, bent by the black hole's gravity into a ring shape. Light from the far side of the disk, which would normally be hidden from view, was bent up and over the black hole, becoming visible above and below the dark shadow. Light from the near side was bent as well, creating a complex layered structure. Scientists call these structures photon rings, places where light has orbited the black hole one or more times before escaping. If you could somehow get close to a black hole and look around, what you'd see would be profoundly disorienting. The sky wouldn't look like the sky. Stars behind the black hole would appear as a bright ring encircling the darkness. Stars to the side would be stretched and distorted. Looking directly at the black hole, you'd see a perfectly circular shadow, and within that shadow, nothing. No light. No reflection. Just absolute blackness, darker than anything you've ever experienced, because it's not the absence of light due to lack of a source. It's a region where light can't escape. Now, bring this back to Earth. Imagine our 10 solar mass black hole drifting into the inner solar system, passing at a distance of, say, 5 AU, roughly the distance from the Sun to Jupiter. From Earth looking toward the black hole, you'd start to notice something strange in that part of the sky. At first, it would be subtle, a faint gravitational lensing effect, barely noticeable to the naked eye. Stars in the region near the black hole might appear to shimmer or shift position slightly, the way stars near the horizon shimmer due to atmospheric refraction, but more pronounced. Astronomers with telescopes would notice it immediately. Stars near the black hole's position would be displaced from their catalog coordinates. The displacement would follow a predictable pattern. Stars closer to the black hole would be deflected more strongly, creating a kind of radial stretching effect, as if the black hole were pulling on the fabric of the star field itself. As the black hole came closer, 3 AU, 2 AU, the effect would become obvious even to casual observers. If the black hole passed in front of a dense star field, like the band of the Milky Way, you'd see the stars bend around it. The black hole itself would appear as a circular region of darkness, but surrounding that darkness would be a ring of light stars whose light had been bent around the black hole's gravity well. It would look like a lens floating in space, distorting everything behind it. This isn't speculation. Scientists have simulated what this would look like using general relativistic ray tracing software. In 2014, physicist Kip Thorne worked with the visual effects team on the film Interstellar to create scientifically accurate images of a rapidly rotating black hole. The result was striking and unfamiliar. The accretion disk didn't look like a flat disk seen edge-on. It appeared to wrap around the black hole in strange ways, with the far side visible both above and below the black hole, and the near side compressed into a bright crescent. The reason is Doppler beaming. Light from the part of the disk moving toward the viewer is blue shifted and brightened. Light from the part moving away is red shifted and dimmed. Combined with gravitational lensing, this creates an asymmetric layered appearance. When audiences saw the black hole in Interstellar, many thought it was artistic license. It wasn't. It was physics rendered as accurately as possible, given what we understand about rotating black holes. For a black hole passing through our solar system, there might not be an accretion disk. Stellar mass black holes drifting through empty space don't usually have one. But the gravitational lensing alone would be spectacular. If the black hole passed between Earth and the Sun, there would be a moment when the Sun's light would be lensed into a ring, an Einstein ring named after the physicist who first predicted it. The Sun would appear as a bright circle surrounding the black hole's shadow, and for a brief time, the black hole would eclipse the Sun in a way no moon ever could. The darkness wouldn't be total. Light from the Sun would bend around the black hole, creating a luminous halo. But the amount of light reaching Earth would drop significantly. Temperatures would fall. Photosynthesis would slow. It would be like a prolonged partial solar eclipse lasting for hours or days, depending on the relative velocities and distances involved. And it wouldn't just be the Sun. The Moon, if visible, would lens into strange shapes as the black hole passed near it. Planets like Venus or Jupiter, normally visible as bright points of light, might appear stretched or doubled if the black hole's gravity created multiple light paths between them and Earth. One of the most famous examples of gravitational lensing, creating multiple images, is the Einstein cross discovered in 1985. It's a quasar, a luminous active galactic nucleus, whose light is lensed by a foreground galaxy. The galaxy's gravity bends the quasar's light in such a way that 4 images of the same quasar appear arranged in a cross pattern around the lensing galaxy. Observing the Einstein cross, you're seeing the same object at the same moment in time from 4 different light paths that took 4 slightly different routes through curved space-time. For Earth, experiencing lensing from a nearby black hole, we might see similar effects on a smaller scale. A distant star directly behind the black hole, from our perspective, might appear as a ring. A star slightly off to the side might split into 2 or more images. The night sky would become a kaleidoscope of duplicated, distorted, and displaced stars. Amateur astronomers would be baffled. Smartphone apps that identify constellations by overlaying names on camera views would fail completely. Navigation by stars, which humans have relied on for millennia, would become impossible in the part of the sky affected by the lensing. And then there's the question of what happens to starlight as it climbs out of the black hole's gravitational well. Light loses energy when it escapes from a deep gravitational potential, a phenomenon called gravitational redshift. For light passing close to a black hole, this effect can be significant. Blue light might shift to green, green to yellow, yellow to red. The spectrum of a star lensed by the black hole would be stretched toward longer wavelengths, making hot blue stars appear cooler and redder than they actually are. Astronomers on Earth, trying to make sense of the observations, would initially struggle. Is that star actually red, or is it red shifted by the black hole's gravity? Is that star in the position we're seeing it, or is its light being deflected? Only by carefully modeling the black hole's mass and trajectory could scientists reconstruct the true positions and properties of the stars being lensed. But perhaps the most profound visual change would be the appearance of the cosmic microwave background, the faint glow of radiation left over from the Big Bang, visible in all directions, with a temperature of about 2.7 Kelvin. Normally, this radiation is nearly uniform across the sky, with tiny fluctuations that reveal the structure of the early universe. Near a black hole, that uniformity would break. The black hole would gravitationally lens the cosmic microwave background, creating a cold spot, a shadow in the primordial light. Research suggests that this effect could be detectable with sensitive instruments. If someone on Earth had a telescope capable of mapping the cosmic microwave background with high precision, they'd see a circular region where the temperature appeared different, distorted by the black hole's gravity. It would be a reminder that the black hole isn't just an object in our immediate vicinity. It's an object that affects the entire observable universe, at least from our perspective. Every photon that passes near it is deflected, delayed, altered. The black hole reshapes not just space, but the information traveling through space. And information is all we have. We can't touch the stars. We can't visit them, at least not with current technology. All we can do is collect the light they send us and decode it. That light tells us what the stars are made of, how hot they are, how far away, how fast they're moving. But if a black hole is bending that, light filtering it, distorting it, then the sky becomes a puzzle with missing pieces and warped edges. There's a haunting beauty to it, though. Gravitational lensing reveals things that would otherwise be hidden. It magnifies distant objects. It creates symmetries and patterns. Some of the most beautiful astronomical images ever captured, like the Hubble Deep Field, which contains lensed galaxies forming arcs and rings, owe their existence to gravity's ability to bend light. If a black hole passed near Earth, we'd lose the familiar sky, the one humans have navigated by and told stories about for hundreds of thousands of years. The Big Dipper, Orion, the Southern Cross. They'd all become unrecognizable, at least temporarily, at least in the part of the sky near the black hole. But we'd gain something too, a direct visceral demonstration that space-time is not empty passive nothingness. It's dynamic, it's responsive. It's a fabric that can be stretched and warped by mass, and light, massless though it is, has no choice but to follow the curves. In a way, we'd be seeing the universe the way it actually is, not the simplified version our brains construct, from the assumption that light travels in straight lines. We'd be seeing the shape of gravity itself, written in photons painted across the sky in arcs and rings and shadows. But even as the sky transformed, even as light bent and stars danced and the sun flickered behind a halo of darkness, there would be one final threshold waiting. One final consequence of the black hole's approach. The place where predictions end and mystery begins. There is a boundary in space where all paths converge. Not a wall, not a surface. Not anything you could touch or see or measure in the ordinary sense. Just a mathematical threshold, a radius around a black hole where the escape velocity equals the speed of light. Cross inward past that boundary, and the future narrows to a single possibility. Every direction you could move, every choice you could make, every path through space-time leads to the same place. The center, the singularity, the end. That boundary is the event horizon, and it's one of the most mysterious concepts in all of physics. If Earth were somehow pulled across it, if our trajectory brought us not just near the black hole, but into it, what would that crossing be like? What would happen in those final moments before the planet dissolved into the darkness? Let's slow down and walk through it step by step, the way a scientist would. The way someone trying to understand rather than just imagine would approach the question. First, we need to revisit what the event horizon actually is. The name is precise. An event in physics is a point in space-time, a specific location at a specific moment. The event horizon is the boundary beyond which events can't influence the outside universe. Light emitted inside the horizon can't escape. Information can't escape. Cause and effect, the normal flow of events from past to future, break down in a way that makes the interior of the black hole fundamentally disconnected from everything outside. The radius of the event horizon is the Schwarzschild radius, which for a non-rotating black hole is given by a simple formula. 2 times the gravitational constant, times the mass divided by the speed of light squared. For our 10 solar mass black hole that works out to about 30 kilometers. The event horizon is a sphere 60 kilometers in diameter, roughly the size of a medium-sized city. 60 kilometers seems large when you think about human scales, but in cosmic terms, it's infinitesimal. The Sun, for comparison, has a diameter of about 1.4 million kilometers. Jupiter is about 140,000 kilometers across. Even Earth, at about 12,700 kilometers in diameter, is more than 200 times larger than the event horizon of a 10 solar mass black hole. Now, imagine Earth approaching that boundary, not by choice, obviously. Perhaps Earth's orbit has been so severely perturbed by the black hole's gravity that we've been captured, pulled into a spiraling trajectory that will eventually intersect the event horizon. Or perhaps the black hole's trajectory has brought it so close that Earth is simply falling, unable to resist, drawn inexorably inward. The approach would not be gentle. Long before reaching the event horizon, Earth would be experiencing tidal forces strong enough to tear the planet apart. We've already discussed how that would happen: the Roche limit, the stretching, the fragmentation. But let's imagine, for the sake of understanding, what crossing the horizon means, that we could somehow hold Earth together. Maybe we invoke some impossible material, some science fiction force field that keeps the planet intact despite the tidal stress. Or maybe we shrink our thought experiment down to something smaller: a spacecraft, a probe, a single atom even. The principle is the same. As you approach the event horizon, several things happen simultaneously, and how you experience them depends entirely on your perspective. From far away, watching through a telescope, you'd see the infalling object slow down. Its motion would become sluggish, asymptotically approaching the event horizon, but never quite reaching it. The light from the object would shift toward longer wavelengths as it climbed out of the deepening gravitational well. Red light would become infrared. Infrared would fade into radio waves. Eventually, the light would be stretched to wavelengths longer than the size of the observable universe, and the object would simply fade from view, frozen at the edge of the horizon, dimmer and dimmer, until it vanished into the background glow of space. From your perspective as an outside observer, the object never crosses the event horizon. It just stops, hangs there, fades away. This is a consequence of time dilation taken to an extreme. As the object gets closer to the horizon, time for it slows down from your perspective. At the horizon itself, time appears to stop completely. 1 second for the infalling object becomes an hour a year, a millennium for you. Eventually, an eternity. But from the perspective of someone falling with the object riding along with that spacecraft, that probe, that atom, the experience is completely different. You don't slow down. You don't stop. Time passes normally for you, exactly 1 second per second, as it always has. You fall smoothly, continuously, and after a finite measurable amount of time, you cross the event horizon. For a 10 solar mass black hole, that time might be a fraction of a second. You might not even notice the moment of crossing. There's no physical barrier, no wall, no sensation of passing through anything. Locally in your immediate vicinity, space-time looks almost normal. You could look at your instruments, check your watch, do calculations. Everything would seem fine, but if you tried to turn around, you discover something terrifying. You can't. Not in the sense that your engines don't work or your thrusters have failed. They work fine. But the direction outward, the direction away from the singularity, no longer exists in your future. It's in your past. You can no more move outward than you could move backward in time. The singularity is ahead of you in every direction, and no amount of thrust, no amount of energy can change that. Inside the event horizon, scientists believe the inward direction becomes time-like, and the time direction becomes space-like. What that means is subtle and hard to visualize, but the consequence is clear. Falling toward the singularity is as inevitable as aging. You can't stop it. You can't reverse it. You can only wait for it to happen. In May of 2024, NASA astrophysicist Jeremy Schnittman released a simulation showing what it would look like to fall into a supermassive black hole with 4.3 million solar masses, the mass of Sagittarius A star. The simulation was created using supercomputers and general relativistic ray tracing to accurately model how light behaves near the event horizon. The visualization shows the view from a camera falling inward, with the accretion disk providing visual reference points. As the camera approaches the event horizon, several things become visible. The accretion disk appears brighter and whiter in the direction of motion. An effect of Doppler beaming light from objects moving toward you is blue shifted and amplified. Stars behind the camera appear compressed into a shrinking circle. Time dilation effects become extreme, and then smoothly continuously the camera crosses the horizon. Once inside, the view changes. The disk wraps around in strange ways. The photon ring light that's orbited the black hole multiple times becomes more prominent. And then, as the camera continues to fall, the accretion disk stretches into a thin ribbon across the field of view. Stars compress into a narrow band. And finally, everything goes dark as the camera approaches the singularity, where tidal forces become infinite, and the simulation ends because the mathematics break down. From crossing the event horizon to reaching the singularity in that simulation took about 12.8 seconds. The distance traveled was about 79,500 miles, 128,000 kilometers. That's roughly equivalent to traveling from Earth to the Moon in less than 13 seconds, except you're falling through spacetime, so severely warped that directions lose their meaning. For a smaller, denser stellar mass black hole, the journey from horizon to singularity would be even shorter, perhaps a fraction of a second, and the tidal forces would be stronger, much stronger, strong enough to shred any physical object into its constituent particles. Stephen Hawking described this process in his book, A Brief History of Time, and he gave it the whimsical name spaghettification. It's not meant to make light of the violence involved. It's just a vivid way to describe what happens when the tidal gradient becomes so steep that an object is stretched into a long, thin filament. Imagine you're falling feet first. Your feet are slightly closer to the singularity than your head, so they feel slightly more gravity. At first, the difference is negligible, but as you get closer, the gradient steepens. Your feet begin to feel noticeably more pull than your head. The difference grows. Your body stretches, your bones elongate, your muscles pull apart, your cells are torn from each other, your molecules are ripped into atoms, your atoms are torn into subatomic particles, and all of this happens faster than you can process it, faster than pain can travel along your nerves, faster than your brain can register what's happening. One moment you exist. The next moment, you're a stream of particles spiraling toward the singularity indistinguishable from any other matter that's fallen in. There's a poetic horror to it. The thing that makes you, your memories, your thoughts, your identity is encoded in the structure of your brain, which is encoded in the arrangement of molecules, which is encoded in the configuration of atoms. When those atoms are ripped apart, when the information about their arrangement is scrambled by tidal forces, you don't just die, you're erased. There's nothing left to bury, nothing left to remember, just energy and mass indistinguishable from anything else absorbed into the black hole's event horizon, adding infinitesimally to its mass. In 1974, Stephen Hawking discovered something surprising. Black holes aren't completely black. Due to quantum effects at the event horizon, they emit a faint thermal radiation now called Hawking radiation. Particle-antiparticle pairs form spontaneously near the horizon, and occasionally one particle falls in, while the other escapes. From an external perspective, it looks like the black hole is glowing, emitting particles very slowly evaporating. For a stellar mass black hole, the Hawking radiation is unimaginably faint, far weaker than the cosmic microwave background, and the evaporation timescale is incomprehensibly long. A 10 solar mass black hole would take about 10 to the power of 67 years to evaporate completely. The current age of the universe is only about 14 billion years, or about 10 to the power of 10 years. So, for all practical purposes, once something falls into a stellar mass black hole, it's gone forever. The black hole will outlast the stars, outlast the galaxies, outlast everything, except maybe other black holes. But there's a deeper question lurking here. What happens to the information? If you fall into a black hole, you carry information with you, the exact configuration of every particle in your body, the state of every quantum field. Does that information vanish when you cross the horizon? Is it destroyed at the singularity? According to classical general relativity, yes, the information is lost, gone, unrecoverable. But according to quantum mechanics, information can't be destroyed. It can be scrambled, hidden, transformed, but the total information content of the universe must remain constant. This contradiction is called the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. Some physicists, including Hawking in his later work, argued that information isn't lost. It's encoded in subtle correlations in the Hawking radiation, emitted over the black hole's lifetime. Others suggest that information is preserved in the structure of space-time itself, perhaps on the event horizon encoded in a way we don't yet understand. The holographic principle, for instance, suggests that all the information about a region of space can be encoded on its boundary like a hologram. But these are speculations, attempts to reconcile two theories, general relativity and quantum mechanics, that don't quite fit together. We don't have a theory of quantum gravity yet. We don't know what really happens at the singularity or at the event horizon when we account for quantum effects. All we have are the equations of general relativity, which predict infinities and singularities and information loss, and the equations of quantum mechanics, which insist those predictions must be wrong somehow. If Earth crossed the event horizon of a black hole, the question of what happens to the information encoded in Earth's structure, every rock, every ocean, every living thing, every memory becomes not just philosophical, but immediate. Does that information survive somewhere encoded in the black hole's properties? Or is it truly destroyed, erased from reality as if it never existed? We don't know. And in a sense, we can't know because anything that crosses the horizon can't send information back out to tell us what it found. But there's one thing we do know. The crossing itself from the perspective of the infalling object is not violent. It's not dramatic. It's smooth, ordinary. It's only afterward, as you continue to fall and the tidal forces build and the singularity approaches, that the true strangeness reveals itself. And by then, there's no turning back. There's only forward, only inward, only the final inevitable collapse into the point where all equations fail and all predictions end. But even contemplating that crossing, even standing at the edge of the event horizon in our minds, there's one more thing worth remembering about black holes. One more truth that brings us back to where we started. They're out there, the black holes. Wandering through the galaxy like silent shepherds, invisible, except when they happen to pass near something bright enough to reveal them. And they're closer than you might think. In June of 2020, a team of astronomers led by Thomas Ravinius at the European Southern Observatory announced the discovery of the closest known black hole to Earth. It sits in a triple star system called HR 6819. Visible to the naked eye in the southern constellation Telescopium. The system is about 1,000 light-years away, close enough that if you could somehow travel at the speed of light, you'd reach it in a millennium. Close enough that the light we're seeing from those stars tonight left them around the time the Vikings were exploring North America. 1,000 light-years sounds far, and it is by any human measure. But in galactic terms, it's our neighborhood. It's our backyard. The Milky Way is about 100,000 light-years across, and we've found a black hole at 1% of that distance. If the galaxy were a city, HR 6819 would be just a few blocks away. And here's what keeps astronomers awake at night in the best possible way: that black hole was discovered only because it happens to orbit two visible stars, and those stars wobble in a way that betrayed the presence of something massive and invisible. But most black holes don't have companion stars. Most of them are solitary, drifting alone through interstellar space, detectable only through their gravitational effects on things they happen to pass near, which means there are almost certainly other black holes closer than HR 6819 that we simply haven't found yet. Some estimates suggest the Milky Way contains between 100 million and 1 billion stellar mass black holes. Most of them formed billions of years ago when massive stars exhausted their fuel and collapsed. They've been wandering ever since, following the slow orbital dance of the galaxy, occasionally passing through regions of higher star density, occasionally interacting gravitationally with other objects, but mostly just drifting silent and patient through the dark. So, what are the odds that one of them will pass close to Earth, close enough to matter? The good news, if we can call it that, is that space is really, really big. The distances between stars are immense compared to the sizes of the stars themselves. If you scaled the sun down to the size of a grain of sand, the nearest star would be about 10 kilometers away. Black holes are even smaller. A 10 solar mass black hole scaled to the same proportion would be far tinier than a grain of sand, more like a bacterium. The Milky Way is about 25,000 light years from center to edge in the disk where most stars live. Earth sits about 2/3 of the way out from the center. In our local neighborhood, within, say, 100 light years, there are probably a few thousand stars and statistically maybe a handful of stellar mass black holes. But even a handful of black holes in a volume 100 light years across means the average separation between objects is enormous. Light years, parsecs, distances so large that even traveling at relativistic speeds, a black hole would take thousands or millions of years to traverse them. Astronomers have calculated the probability of a star passing within 1 light year of the sun. It's about one event every few million years. The last known close approach was about 70,000 years ago, when a red dwarf called Schultz's star passed through the outer reaches of the Oort cloud, the shell of icy objects surrounding the solar system, at about 1 light year from the sun. It didn't cause any noticeable disruption, just a gentle gravitational ripple that might have nudged a few comets slightly inward. For a black hole to pass that close within 1 light year, the odds are much lower simply because black holes are rarer than stars, maybe one event every few hundred million years or longer. And for a black hole to pass within 5 or 10 AU, close enough to significantly disrupt Earth's orbit and cause the kinds of effects we've been discussing, the odds drop to perhaps one event in many billions of years, far longer than Earth has existed as a planet. Which means that in all of Earth's 4.5 billion year history, it's unlikely we've ever had a close encounter with a black hole. And in the remaining time, the sun has left another 5 billion years or so before it exhausts its hydrogen fuel and begins to swell into a red giant. It's unlikely we ever will. Does that mean we're safe? That black holes are interesting in theory, but irrelevant in practice? Not quite, because safety isn't really the point of thinking about these things. Understanding is. We live on a small planet orbiting an average star in an unremarkable region of a typical spiral galaxy. We're not special in cosmic terms. We're not protected by anything except distance and probability. The universe doesn't care about us. It doesn't arrange itself for our convenience. Black holes exist not because they're necessary for life or consciousness, but because the laws of physics allow them to form, and so they do. Supernovae explode, stars collapse, space-time curves, gravity pulls. These things happen regardless of whether anyone is around to observe them. But here's the paradox. The very fact that we can observe them, that we can ask questions about what would happen if a black hole passed near Earth, that we can calculate probabilities and simulate outcomes, and understand the physics is itself extraordinary. We are matter that has become aware of itself. We are atoms arranged in such a way that we can contemplate the nature of atoms. We are products of the universe that can study the universe. And one of the things we've learned through centuries of observation and mathematics and argument and discovery is that the universe operates according to rules, not arbitrary rules, not rules designed for our benefit, but consistent, elegant, comprehensible rules that apply everywhere to everything from the smallest subatomic particles to the largest galaxy clusters. General relativity works near black holes exactly the same way it works near Earth. The inverse square law of gravity applies in the Andromeda galaxy, just as it does in the solar system. The speed of light is constant, whether you're on a planet or falling toward an event horizon. That consistency is what makes science possible, and it's also what makes stories like this one possible. We can imagine a black hole passing near Earth, not because we've experienced it, but because we understand the principles. We can extrapolate, we can calculate, we can predict with reasonable confidence what the consequences would be, even though we've never seen it happen, and probably never will. In 2015, when LIGO detected gravitational waves from merging black holes for the first time, it confirmed a prediction Einstein made in 1916, almost exactly 100 years earlier. Einstein never expected gravitational waves to be detected. He thought they'd be too faint, the effects too subtle. But he was right about the physics, and a century later, technology caught up to theory. The universe was doing what the equations predicted even when no one was watching, even when no one could measure it yet. That's the power of understanding. It lets you see things before they happen. It lets you prepare, or at least imagine preparing. It lets you ask, what if? And follow the logic wherever it leads. So, what if a black hole did pass near Earth? What if, against all odds, the trajectory of some wandering stellar remnant brought it through our solar system? We've walked through the consequences: tidal forces stretching and heating the planet, orbits destabilized, the moon lost, earthquakes and volcanoes, time dilation, gravitational lensing, the sky transformed, and ultimately, if the approach were close enough, the possibility of crossing the event horizon of Earth itself, being drawn into the darkness and dissolved into particles and information that might or might not survive in some form we don't yet understand. It would be the end of everything we know, but it would also be the ultimate physics experiment, the ultimate test of our theories. If anyone were around to observe it, to measure it, to record it, they'd learn more about gravity and space-time and the nature of reality in those final hours or days than we've learned in all of human history. Of course, no one would be around. That's the irony. The most profound event in Earth's history would happen without witnesses, or at least without survivors to remember it. The knowledge would die with the planet, unless it didn't. Unless someone somewhere far enough away could watch, could record, could preserve the data and the story. Maybe future civilizations, millions of years from now, will have spread throughout the galaxy, and they'll have instruments sensitive enough to detect and study such events from safe distances. Maybe they'll watch planets fall into black holes the way we watch stars go. Supernova, tragic, violent, beautiful, and instructive. But for now, for us, the story is hypothetical. It's a thought experiment, a way to explore the edges of what we understand and what we don't. And the truth we come back to, the truth that's worth holding on to, is this: black holes are not monsters. They're not evil. They're not hunting us. They're just objects obeying the same laws of physics that govern everything else. They're dense. They're extreme. They warp space-time more than anything else we know of. But they don't suck. They don't seek. They don't have intent. They simply are. And most of them are far, far away. Far enough that we can study them, learn from them, be awed by them, without ever being threatened by them. The closest black hole is 1,000 light years away. The next closest might be twice that distance, or half. We don't know yet. We're still searching, still cataloging, still mapping the dark spaces between the stars. Every year, new telescopes come online, new surveys begin, new black holes are found their positions, and masses measured their histories inferred from the light or lack of light they emit. And every discovery is a gift, a piece of the puzzle, a window into how the universe works at its most extreme. There's a line from the poet Rainer Maria Rilke that seems fitting here. He wrote, "Perhaps all the dragons in our lives are princesses who are only waiting to see us act just once with beauty and courage." Black holes are not dragons. They're not princesses either. They're phenomena. But the sentiment holds. The things we fear when we understand them become less frightening. Not safe, perhaps. Not tame, but comprehensible, knowable. Part of the natural order, not supernatural terrors lurking in the dark. A black hole passing near Earth would be catastrophic beyond anything we could survive. But it's also unlikely beyond anything we need to worry about. The odds are astronomically small. The distances are vast. The universe, for all its violence, is mostly empty. And the empty parts are what keep us safe, so we can rest. We can sleep. We can go about our lives under these patient stars, knowing that the darkness, while real, is distant. The black holes are out there, yes, wandering, waiting. But they're not coming for us. Not tonight. Not in our lifetimes. Not in 1,000 lifetimes. And that's a kind of mercy, isn't it? The mercy of distance, the mercy of space being so large that even objects as massive as black holes rarely collide with anything. The mercy of living in a universe governed by laws that we can, with effort and time, come to understand. We've traveled far tonight, you and I. From the architecture of event horizons to the bending of starlight. From tidal forces that break worlds to time that slows and stops. From the geological tremors of a planet in distress to the final crossing of a boundary beyond which nothing returns. We've asked difficult questions. We've followed the mathematics into dark places. We've imagined the unimaginable, not to frighten ourselves, but to understand, to see clearly, to know what the universe is capable of, even if, especially if we never experience it ourselves. That's what science does. It takes the unknown and makes it known. It takes the fearsome and makes it understandable. It doesn't always make things less frightening. Sometimes understanding reveals just how fragile we are, how contingent our existence is on circumstances we can't control. But it also reveals how much we've learned, how far we've come, how much we're capable of comprehending when we choose to look closely, think carefully, and face the darkness with curiosity instead of dread. So, thank you for walking with me through this thought experiment. Thank you for listening, for wondering, for letting yourself imagine a world changed by forces we barely understand, but are learning to predict. Thank you for being here in this quiet moment, thinking about black holes and Earth and the spaces between stars. The universe is vast, the night is long, and there are always more stories waiting to be told, more questions waiting to be asked, more mysteries waiting at the edges of what we know. Sleep well knowing the darkness is far and the stars still shine. Until we meet again under these same patient skies. Good night.